Can you not? Ayun mo.
हाय तो अर्कर आहे अर्कर आहे प्रोफेसर येतो मानस कमल IIT गुवाहाटीचा आहे. मागच्या वेळेचं आमचं IIT कलकत्ताचं खडगपूरचं होतं. यावेळेचं IIT गुवाहाटीचं आहे.
IIT गुवाहाटी.
Good evening, sir.
Yeah, good evening. So we can start from 6:10. So let us wait for 5 to 6 minutes, then we can start.
Okay, sir. Okay.
Okay, so I think now we can start the session. So welcome you all to the week 13 live session on the course entitled Machine Learning and Deep Learning Fundamentals and Applications. So in this particular week, as because the uh, week week 12 quiz is basically live and the content is also live too. So therefore, I will not be able to solve the actual quiz questions. And at the same time, in the last class also, I dealt with the CNN based quiz questions. So they were practically the practice questions that I have solved. And majority of the practice questions that I have solved, they are quite similar to the questions that have been asked in the week 11 quiz. So I hope uh, now it will be easier for you to solve the live quiz that is there in week 11 tab. And so far as the week 12 content is concerned, in week 12, Professor N.K. Bhuyan has discussed the basics of generative adversarial network. At the same time, UNet, which is basically used for segmentation, image segmentation. And he has also discussed about autoencoders in general. So we have seen that there is a concept called PCA, which is basically used for dimensionality reduction. And the PCA was kind of a linear transformation. That is what we had done in case of PCA. But in case of autoencoder, it basically facilitates the nonlinear transformation via uh, convolutional neural network or in general multi-layer perceptron based deep learning architectures, which helps in better data dimensional reduction in a real sense. Now, in this particular live session, we will basically focus on the implementation of three different architectures. Uh, One is the UNet architecture. So UNet basically it is used for the image segmentation. So uh, we'll be implementing UNet through convolutional neural network architecture. Will implement a small unit architecture? Unit can be a very large network as well, but so far as the just to show the implementation part, I will just take a small unit example. Then we have also seen the RNN. Sorry. Yeah. So we have also seen RNN, that is called recurrent neural network architecture, which basically deals with the time series type of data, time series data modeling. So over here, in case of RNN, there's a specific set of neural network architectures are there, which is basically called LSTM, which is a very popular one. So uh, RNN also includes some other neural network architectures, which is called GRU, which is also named as gated recurrent unit. Then you have LSTM, that is long short-term memory. Then you have bidirectional version as well, so which is called bi-LSTM. That means bidirectional LSTM, and the bidirectional version of GRU as well, which is named as bi-GRU. Okay. So we'll basically see how to predict some data using LSTM. LSTM, already we have seen in linear regression, we basically try to predict some real data, real valued data. So LSTM is also used for that particular purpose, but in linear regression, it was sort of a machine learning based approach. You had a proper mathematical formulation for that. You had W transpose into X plus bias. That was the prediction, which we called as Y-pred. And then we used to take the minimum mean squared error loss, and that has to be minimized to get a good prediction. So that was so far as the linear regression is concerned. Now, in case of LSTM, as because it's a neural network architecture in a non-linear fashion, you can do the same operation, and it is meant to deal with a larger volume of data, and therefore you can train on a bigger data set, and you can you may basically get good result representation as well in case of deep learning based LSTM architecture. Then we'll see that the implementation of a convolutional autoencoder architecture. So, and the specific purpose of this autoencoder is basically denoising. So if I just want to show you what is the purpose of this denoising autoencoder, let's say you have MNIST dataset. Yesterday I trained two neural network architectures. One is LeNet 5 and another one is VGG16 on uh, MNIST digit dataset. So MNIST digit dataset contains 60,000 training images and 10,000 testing images. And at the same time, the images are basically handwritten digits of 0 to 9. So a total of 10 digit types are there in MNIST dataset. Now let's say the images were quite clean. You had an image of 0, you had image of 1, 2, 3, like this. Now if I just tell you, now if I just give you another data set and basically what I'm doing, so the images, let's say I am annotating these images as X. What I am doing in the next is I'm adding Gaussian noise. So all of these images are basically passed through this particular block, which is basically a noise addition block. And therefore, after addition of noise, your images are basically looking like this. So you had a 0, but now it is buried into noise. So the image is now quite noisy image. So this is called Y noisy. So the equation is Y noisy is equals to X plus, as because we are adding Gaussian noise or normal distribution based noise. So I can write 0, 1. So that means mean is 0 and variance is equals to . So now we had this image. Now we have added the Gaussian noise or normal distribution based noise, and then we have got a noisy output. Now the problem at hand that I'm providing is the problem statement is that reduce the problem statement can be can you retrieve the clean images from the noisy images. So that means the question is, now we have got this noisy images. Now from these noisy images, can you get the clean image? So the problem is also referred as a denoising problem. So what we will do is we will take this image, and we know that autoencoder has a structure like this. I will give the X, Y noisy data. It will transform into a reduced dimensional representation, which is also called the bottleneck. And then I will expand the dimensions again, and it will again try to create a copy like this. Which is X. And we know that what is the loss function of an autoencoder? So the loss function is basically MSA. So 1 upon n, it will run in the order of I. So yn I minus xi square. So I'm sorry. So it will actually try to predict x hat. So given this image, it will try to produce a cleaner version. And then I will basically calculate the error between these two. We have, this is true clean, and this is your predicted clean. So that means your autoencoder takes a noisy image, it tries to produce a clean image, and then we have to take the loss between the predicted clean image and the original or the true clean image. So therefore I can write x hat I minus xi, or vice versa. I can put minus over here. I should not write comma. And the problem is, now the problem I can formulate. So this is the encoder weights and this is the decoder weights. One second. Yeah, so we have this, this is the loss function, and the optimization that we will do is minimize this loss argmin of L, and we will update these weights. So therefore WE comma WT. So this is the problem that we will try to simulate in Google Colab platform through Python language. And the new, this architecture over here, this autoencoder architecture, as because this is now implemented for denoising purpose, so this is called denoising autoencoder. And inside this denoising autoencoder, we will be using convolution blocks to create the autoencoder architecture. Fine. And unit already you have seen in week's lecture as well. So I don't think so that you need any introduction for that. So now let us directly start simulating the structure. So let me just take one unit image. It will be helpful to discuss. So we can just discard this particular thing. Yeah. We can discard this thing because this is based on the other person who has created this particular image. It is based on their convention. We will not use this particular convention. Okay. So UNet is basically this sort of a neural network architecture, which is basically working on the concept of encoder, decoder, and then at the encoder side, you will have an image, and at this side, you will have the masked image or the segmented output. And it actually looks like this. Yeah. So it can be thought of like this. So over here, you have the original image. So which is basically this one. So this is the original image. And this is the segmented output that you will get over here. And this is basically this thing. Now we have to simulate this sort of architecture again in using Python. So now let us start the coding part. So I have uploaded this code already. Sorry. I have already uploaded the code in my GitHub profile. So you can also just open the GitHub profile and should be okay, fine. So first what we will do, we will install TensorFlow. So I am specifically running on a specific version, that is pip. To install TensorFlow or any other libraries, what you have to write, that is uh, exclamation mark pip install, then the library name and the version. Each and every library or each and every package has a corresponding version, specific version. So for example, currently TensorFlow is at 2.17.0. So I am specifically running on this particular version. So it will take some time to download the uh, TensorFlow version. And you will see after some time it will write that it is uninstalling the current TensorFlow and downloading. So yeah. So over here, see uninstalling the TensorFlow board 2.17.0 because that is the current version of TensorFlow. I'm basically downgrading the TensorFlow version. So let us wait for a minute. And yeah, runtime is also GPU. So it will enable us to run the code in a more faster way. And then I am importing the libraries. So we already know that from import TensorFlow as TF. Then I am importing Keras from TensorFlow. So TensorFlow import Keras. Then I need to import the layers because already you know that we'll be using convolution layers. So therefore I'm writing from TensorFlow.keras import layers. So within layers we have con 2D, then max pool 2D, average pool 2D, like that. Then import TensorFlow datasets as TFDS. So last time we imported NIS dataset. Now we'll be using this TFDS. Sorry, this is the TensorFlow dataset. So I'm not gonna write TensorFlow underscore dataset again and again. So I'm writing it as TFDS. Now from TFDS, I will basically take some of the dataset which is basically required for this particular demo. Then I'm importing matplotlib to plot something and numpy for in general basic array operations. Okay. Then we have to load the data set. So now see, to load the data set, what we have to write? We have to call the object of the data set, that is TFDS, then dot load. And then within the load function, we have to write that whatever data set that we want, we have to give the information. So see, we need Oxford triple IT underscore pet. So this particular data set was published in CVPR conference and they have uploaded in Keras. So therefore we'll be using, we'll be downloading this particular data set to simulate the unit model. So now let us hit the download button. So now you can see that the data set has now been started downloading. So based on your internet speed, it might take some time. Yeah, so now the data set has been downloaded. And now we can print the information of the data set, that you can see that where the data set. So this is the home page of the data set. This is the image. This data set contains images of pets and their corresponding masks. So this is basically an object segmentation task. So you can see that we are basically, we've been given the images and we have to segment out the where the object is located in the image. So for example, over here as well, this is the image, this is the position of the pet that we have to segment it out. So it has numerous amount of pets and the metadata is already present, that you can see that it has different breeds of cats and dogs and the other information that you can look into. So total size of the data set is 773 MB. And this is the corresponding paper citations. So this has been published in IEEE CVPR conference. Okay. So now the data set that have been given. So the data set images of high resolution, that is for sure this is an 3-channel image because we are dealing with color images. So there will be R, G and B channels. And at the same time, the image size is quite high, that is 224 cross 224 cross 3. So to reduce the size, what we are first doing is we are resizing the image into shape of 128 cross 128. So initially the shape was 224 cross 224 cross 3. That we are reshaping to 128 cross 128 cross 3. And that's because we are basically downsampling the images. So so what sort of method we'll be using? So there are n number of methods are there to downsample. So over here we are using the pixel based nearest pixel based interpolation. And for the image as well as for the mask, so I have told that we have been given the images and as well as the mask. So as we are downsampling the image, we have to downsample the mask as well. So that is what we are doing over here. Then I have put a augment function. So augment, what we will do. So the data set, if some of the data set has less number of images, so then we synthetically increase the data. So synthetically increasing data size is called augmentation. And for instance, what could be the example of an augmentation? Let's say you have an image of a cat and you tilt the image. So you tilt the image. So this is called rotation based augmentation. Then another thing you can do, you can crop the image. So let's say you just crop this particular part and rest of the things you just have deleted. So therefore it is like this. Rest of the positions are black only. So this is called crop based data augmentation. So now let us see that what sort of augmentations we have done. So what I have used over here is we have used flip based augmentation. That means we are using some sort of a rotation based augmentation, right? For both the input image as well as the mask. Because whatever transformation we are applying into the image, we also have to apply it into the mask as well. Otherwise, we'll not be able to create the genuine prediction. Then what I am doing for all the images and mask, I am using normalization. And normalization in the last class also, I told you that how we can do normalization. The images are having the values in the range of 0 to 255. So therefore, I can divide it with the maximum value. So that is, we can divide with 255 and we want the data type should be float. So therefore, it can take the non-integer values. So that is why I am keeping the data type as tf.float32. That means TensorFlow.float32. And the same we are doing for the input mask as well. Okay. So now in the next stage, what I am doing, I have already written the codes for augmentation, then normalization and resizing operations. Now I have to load the data. So I have written different functions for the training data as well as the testing data. And see what I have done. So input image is basically data point and the instance is image and mask is basically coming from the segmentation mask instance. Then on both the image and mask, sequentially we have to resize it, then augment it and normalize it. So that is what we are doing. And it will basically return the input image and mask. So that means first it will do resize operation, then it will do augmentation, and then it will normalize the image. And the final result that will get is basically after the images, after normalization operations. And for the test data as well, first I am taking the input image and input mask from the image and segmentation mask instance, and thereafter I am resizing and normalizing. So one important point is we perform augmentation only on the training data. So the analogy could be, so for example, if you are teaching mathematics to a kid and he has to give certain exam after 15 to 16 days. So in the examination, only a selected number of questions will be asked. So let's say within 1 hour, only 15 questions will be asked. But this kid has a span of 15 days within which he will basically learn mathematics, and then on the 16th day, he will write an exam. So what you will do as a teacher in these 15 days, you will basically ask that kid to solve numerous amount of problems. So that means this 15 days is the training period of the kid to learn mathematics. So therefore, within this 15 days, you will try to give him all possible types of mathematical questions. So that means you are increasing the number of samples within the training date, within the training phase, which is also basically mentioned, which is also basically referred as augmentation, because augmentation means you have lesser amount of samples, you are increasing the samples by using some sort of affine transformation like rotation, crop, etc., etc. But at the test time, you you do not need augmentation, because at the test time you have been given a specific set of data on top of which you have to use your knowledge based on the you have to use your knowledge based on what you have learned within these 15 days, or in our case this is the training phase, or from the augmented data. So therefore, at the time of training, we need more and more amount of sample to learn from the data. So therefore, augmentation is required. But after training, your model has learned. So now there is no point of augmentation. So we have run this particular part. Now what I will do, I will just load the train data. So from data set, already we have incorporated data set from tf.load. So using tf.load. Now within dataset, I have two folders. One is train and another is test. So I will just load them. And then I will take batch size 64, buffer size 1000. Already these things already we have talked in the last class. What is meant by batch size, because we do not want to feed all data at a single time into the model. We need a specific group of data. We'll sample a group of data from the original data set, and then we'll feed that particular chunk of data into the model. So I have created training batches, validation batches, and test batches. Now, if I just have to show you that how the images look like in the data set. So for that, I just have wrote a for loop, which will basically show you the input image, true mask, and predicted mask. Mind it, as because we are not still done with the prediction, or we have not done any training of the model. So therefore, we will not get any prediction output, but we can get the input images, because from the data set we can get the input image, and at the same time, true mask is basically the mask that have been given in the data set. So for example, now what we'll get a input image like this and the corresponding mask. So now let us see. So see, over here we have an image of a dog, and you can see that it has different foregrounds and backgrounds. So for example, in the foreground we have probably it is somewhat a heap of sand or something, and in the background we have sky, and there is a tower as well. And this is the true mask, and on the true mask what we have is the uh, the mask corresponding to the dog, and rest is the background is basically uh, given with some arbitrary data, or it has been hashed. So we can see some other instances as well. Yeah, see, there is another dog, and this is the true mask of the object. And here the object is basically the images of the pet, and all the background and foreground information have been removed. Okay. So now we need to configure the unit block. So in the current unit that I'm basically trying to simulate, we have two convolution layers. So this is con1 and this is con2. So these I have named as double con block. So I have written this function first. So you can see from here. So def, so I'm creating a function double con block, which will take images as an argument and number of filters that I can define. So what it will do? So it will feed the data into this convolution block. So layers.con2d, and then the n filters, because we can define the number of filters by our own. Then 3 means the kernel size is 3 by 3. Padding is same. Activation function is relu. Then we have used kernel regularizer. So we have used kernel initializer as key uniform. So that means in each and every kernel, we have number of elements to be learned. And how we can initialize them? We can start initialization as a random initialization using the Gaussian distribution. Otherwise, in this case, we are using key normal as the initializer. And then we are passing the input data, which is X. Then the output is also I have named as X. Now this output, it will be passed to the next convolution layer with same architecture, that is n filter, kernel dimension is 3, padding is same, activation is relu, and it is taking the previous layer's output X as an input. And then what it will do, it will return the final convolutional output, which is again, I have named it as X. So I can write return X. Okay. Then I have added downsampling block. So this is max pool. So already we know that pooling layer basically helps to reduce the dimension of the feature maps that we can get from the convolution block. And then I have added a dropout layer. So this acts as a regularizer. You can omit this too. So this is the downsampling block. Okay. So see, downsampling block takes X as an input and number of filters you can define. So first what you are doing, F is equals to double conf block X comma n filter. So that means what you are doing effectively, you are feeding an image which is named as X. It is going to the double convolution block, and the output that you are getting, I am naming this as F. So therefore you can see that you had input as X, you are getting output as F from the double convolution block. Then you are passing this F to max pool 2D with kernel dimension 2 cross 2. So this will reduce the dimension of the activation map that you get from the double convolution block. And then I'm passing it to a dropout layer, which acts as a regularizer term. And I'm returning this F and P. Why? Because I have to pass this into the next segment in unit, which is again create a structure like this. So this is basically P. P will be passed through the next block. And you know that as because unit is a structure like this, you have to add something in this last layer as well, or the corresponding transpose position layer as well. So therefore, we will pass this F to the addition layer in the unit structure. So therefore, we need to return this F as well as P. So from this diagram also, you can see that P will be passed from here and F will be propagated to this so that you can add these two. So over here, you are adding these two. Okay. Then similarly, we need an up sample block, which is to be placed in the con 2D con transpose position. So therefore, I can take an image X, then I can pass it through a con transpose layer with similar sort of arguments. Then I am concatenating X and con features. Con feature is basically this F. Subsequently, you'll see. And then I have added a dropout layer and again a double convolution layer. Okay. So now we are ready. Now we are at a position to start building the unit block because these are the helper functions. So we have configured each and every helper function like double con block, then downsample block, as well as the upsample block. Now we can create the double unit architecture. Sorry, the unit architecture. So I can feed the input. So layer dot input is basically specific. It will specify that it is a input layer. And the shape of the input is 128 cross 128 cross 3, as because we have already seen that we have reshaped these images from 224 cross 224 cross 3 to 128 cross 128 cross 3. Then I'm passing through the fast encoder block, which will basically downsample. So F1, P1 is basically downsample inputs, 64. So that means the filter dimension in the first block is 64. Then what will happen? As because already I have told that P will be propagated to next downsample block. So therefore, you can see that F2, P2 downsample block, the input or the argument of the downsample block is now P1, which is the output from the previous layer, previous downsample block. And the number of filters I have chosen 128. Then again, the third block, which takes P2 as the input, and fourth block, which takes P3 as the input. Now we have to create the bottleneck because this works in the realm of encoder decoder architecture. So therefore, we have encoder side, we have another the decoder side, and we also have a bottleneck side as well. So in the bottleneck, what I am doing, I'm using again a double convolution block, which takes P4 as the input, and the number of filter is 124. So now from the bottleneck, we have to configure the decoder structure. So this is the structure of the decoder. So now you can see the upsampled output is basically upsample block. Bottleneck output it is taking as the corresponding input, and the second convolution feature map that it is taking, it is F4. So that is what I have mentioned, that you need this F to be passed into the decoder architecture. So therefore, we actually need this F as well as P as the output of the downsample block, which can be further added in the decoder part. Then at the same way, I can pass through next upsample block, which will take U6 as the input, and it will take the corresponding F3 as the convolution feature map, and then 256. So you can see that whatever filter dimension you have kept at F3, that same thing should match. Otherwise, you cannot add the element wise summation. Then the third upsample block, which takes U7 and F2, and in F2 you can see uh, the dimension of filter is 128. So therefore, we have kept same 128 dimension. And the last one, U8 and F1, that means it is taking the result from here, and the dimension is 64. So we have kept 64. So now we have to generate a 3-dimensional from this U9. We have to generate a 3-dimensional image because our mask is of 3 dimension. So therefore, I'm again writing a layers.con 2D with number of filters to be 3. So it will take this 64-dimensional data and it will convert into something by something into 3. So that means it will create a 3-channel image. And the filter dimension is 1 cross 1. So that means it's a point-wise multiplication. And then padding is same, activation is softmax. Why activation softmax? Because we know that we want to create the prediction of the mask, and the mask is nothing but 0 and 1. So therefore, we can predict using softmax, which will create a probability distribution ranging from the, as because it is a probability distribution, maximum value is 1. And then we can finally write unit model and configure the model using tf.keras.model. So this function takes 2 arguments. One is the input and another one is the output. Already we have referred that what is input, so that we can write it over here. And we have already defined output as well. So we have written output. So now the unit model will know that what should be taken as input and what should be basically predicted as an output. And we are naming this model specifically as unit. And then as because I need this particular model to be returned from this function, so I have returned unit model. So I can call this function and take the summary. So I just do that. See, this is the model that we have created. On the contrary, you can plot the model image as well. So I can copy the image and let me just try to plot it here. I don't know whether I can rotate the image or not. So you see that it is, even though it is not very clear, but you can see that this is the structure of, sorry, this is the structure of unit. You had something out from the yeah. So you can see you had something out from this downsampling block. So like this, you create something like this. And then you're adding this to the decoder side. And then you are creating a U-shaped architecture. So it is like this. This is the U-shaped architecture. And this is the connections from encoder to decoder. So this is, in a way, this is the ultimate structure of the unit architecture. So this you can see when you will basically simulate the model at your side as well. So you can just download the image and you can investigate what is happening there. And now I can compile the model. Already I have told you that how to compile. We need to specify the optimizer. We need to specify the loss function, and we can check the metrics. So in this case, we will check metrics as accuracy. Now I have to train the model. So that means I have to write model.fit. So number of epochs. So I have to feed the training data, number of epoch. Then steps per each epoch. That means how many iteration it will go in each epoch. Then at the same time, validation steps, and we need to provide the validation data. So in validation data, what we are providing the test data, right? Now let's say, let me take 15 epochs, and then we can train the model. It will take 10 to 15 minutes to train. So let us wait till then. I think I should make it 5 epochs and then train. So not even 5, let's say 3 epochs. So you can change the number of epochs and you can train it at your side. You can train with higher number of epochs, but let us uh, train with smaller number of epochs, so it will not take much of a time. Obviously, the results will not that good because we are running for only 3 epochs, and the total number of data that we have is around 60,000 or 70,000. So obviously, the performance will not that good. So see the validation, the accuracy is around 62%. So if you train with larger number of epochs, the model will eventually learn to how to uh, predict the mask images correctly. So therefore, with larger amount of epochs, you may converge the problem very well. Now let us wait till epoch 3 and then we can again start doing the analysis part.
Yeah, hello, Arka.
Yeah.
Yeah, this is Someshwar here. While it's continuing with the training part,
Yeah.
yesterday we saw that we have trained using the lineate model, right?
Yeah. Yeah.
So what I've done actually, just to make it visually appealing, or even in such cases when we actually wait for model getting trained, I have
Yeah.
added couple of steps for it to visualize the training and the testing error. So if you feel good, I can share that screen and showcase that how we can actually further visualize the training losses and the things that will help our students to understand it better. Can
Yeah,
we do
yeah,
that?
that we can do. That we can do.
Sure.
Let
So let me
me,
just,
yeah. So let me stop share and then you can share your screen.
sure, sure. Yeah. Can you see my screen?
Yeah, yeah, I can see the screen.
Yeah. So this is the code that we implemented.
Yes.
There are some modifications made to the code to visualize the data. So it is implemented using TensorFlow again. We have loaded the data set here, MNIST data set. Then we have modeled it using the lineate architecture,
Yes.
compiled using the Adam optimizer, and the losses are calculated using categorical cross entropy.
Yeah.
We also printed the model summary here, and the portion you see from here that it will update. So essentially, if we know that during training, it we define the batch size here and the epoch size, right? So what
Yeah.
it does essentially during each batch, it will calculate only training losses, right? Because the validations will be done once the entire training batch is completed. So we
Yeah.
cannot plot anything during the batch processing is going on. So we calculated only, captured only training losses and the training accuracy. And once the epoch has finished, the particular epoch has finished, we have calculated the validation losses and the validation accuracy also. So that code is here, that update plot on the batch end and update plot on the epoch end. These are the two functions which are defined. And we also added one class here, plot class, plot the losses, which we will call during our training here as a callback. So in the callback,
Yeah. Yeah.
we
Hmm.
have called the plot losses. So these are the classes it will call initially, and then in turn it will use those two functions to plot the multiple things. So if we see this in action, this is how what we get here is during the training, it will keep on printing the training loss and the training accuracy. We can see that it's converging here, and the
Converging.
training
Yes.
accuracy is increasing. So, and during after every epoch, it will also calculate the validation loss and the validation accuracy.
Yeah.
And then after the entire training, probably I just printed the how the data set looks. Then I also printed the confusion matrix here, where it will show that how many true labels were predicted truly. So if you see
Yeah. Yeah.
this on your
Confusion matrix
x-axis,
we have also
confusion
done.
matrix, yeah. And then also I printed the ROC
What
curve
is it?
that,
Yeah.
yeah. So more it is on this side, we see that it's getting perfectly trained, and we can see here almost 0.9998. So the model has really worked well and predicted the expected output. So these are the things. Let's see this in action now. If we see this in action, if we run this, and this is the model summary that we use for Linet, and then now it has started the training. So if we just go this in full screen mode, you will notice that I have used the clear output. So
Hmm.
it will keep on showing after every batch. For example, here we have 24 batches, right? Where I have defined the um, batch size as 2000. It has generated only 24 batches here. So
Yeah.
likewise, we can keep on like this will keep on like refreshing
You
itself
can
after
play with those values. So either you can increase or decrease the number of
decrease based
batches.
on the conversions. Absolutely. So these are some of the 2 cents from my end till we're waiting for that. And see after every epoch, then it will also give us the
Ah.
validation loss. This will continue. So that is it from my end. So thank you
So
so
what
much for
you
providing
can
this
do,
opportunity.
you can share this IPyNV file with me as well. So I will upload
Sure.
in the GitHub so that students can also basically run this at their side as well.
Absolutely, I can do that. So if you can mention your email ID, I'll just send it to you, or we can right away share it actually. Do you
Yeah.
have your Gmail ID?
Yeah.
So if you can just give me your Gmail ID, I have stopped sharing right now. Okay. So let me first stop.
Let me
Running.
share. So now my screen is visible, right?
Yes, we can see your screen.
Okay. 1 second.
So I locate this file, which is usually the Google Collabs stores all our files into the Google Drive. So
Yeah. So
that
from
way it
here
becomes
also
very
you
easy.
can download, open that notebook, then go
Right.
to file and then
Yeah.
download. And
This
then
is one way
download
of
the
doing it.
IPyNB. The
Correct.
IPyNB.
That's correct. This is one way of doing it. Otherwise, just go to the Google
Just
Drive
go to Google Drive and from
and
there
then we
also
can
you can
share
download.
it. Okay, so right now I'll just go ahead with your way. I'll just download it and then share
Uh,
with you.
and let me just share my
Gmail ID, if you can
email.
give your Gmail
Yeah.
ID.
Can you see the chat?
Yes, I can see the chat. Is chat enabled? Actually, I'm not able to see the chat here.
Okay. So probably that's the issue. Let me just write it over here because it's
Yeah, you can just spell it here,
an
then I probably, yeah.
institution. Mm, yeah. Let me just write it. Arca underscores. So all are in small.
Okay, let me just type it straight away. 1 sec.
2121 double E 34 at the rate ITP.
So it's Arca,
A underscore
ARKA, ARKA, Arca underscore
2121
2121. Okay.
double
Double
E
E 34. Okay. Double E 34. Okay. @
IITP.ac.in.
Will it allow the external also, or it
Yeah,
probably expect?
you are mailing me, right?
No, I'm just sharing it on
Oh,
Google.
okay. Okay, you are sharing, bro.
Okay,
So you
give
can
this also. I'll keep this as a reference for the future communication.
yes. Sure. So this is the Gmail ID.
Yeah. File new. Now, so it's ARKA underscore 2121 double E 24 @ iitppatna.ac.in and ROI ARK 457. 57@gmail.com. Yeah, so I'm sharing this to this particular email ID.
Okay, okay, fine. Okay, so now the iterations have been completed. So we ran this particular model for 3 iterations, and you can see at the third iteration, we got 77.7% accuracy. So you can increase the amount of accuracy by increasing the number of epochs, because now it has only been trained for 3 epochs. So obviously the performance will not that good. So now after training the model, you have got the weights, which is basically updated using gradient descent rule. Now we are good to go with the prediction. So now we can feed the test data and try to visualize that how well your model is basically generating the masks. So you have the ground truth masks or the reference masks on which you have trained your model from the training data. Now you have the test data as well. In test data, you have test images and corresponding masks. So now what we will do, we'll feed this test data to unit architecture. Unit architecture will give you an output of the predicted mask, and then we'll try to calculate the error between them. We'll try to visualize them, how the true mask looks like and how your model is basically predicting. Obviously, your model will not be able to predict much of a good shaped mask because its accuracy is 77% and it has been trained with 3 epochs, but still we can see that how it basically looks like. So what are the functions that we need for that? So again, you can just omit this. I kept the libraries again. Import TensorFlow as TF, import Matplotlib as PLT. You can omit this because already we have instantiated them. So I can comment them. Then I'm creating the following functions. The create mask. So create mask will take the argument as the predicted masks. Then what it will do? So we know that at the output of the what you call the unit architecture, the last layer had if I just show you from here, last layer had a activation of softmax. So softmax means each and every value is basically mapped in between 0 to 1, as because softmax gives you a probability distribution. So now, as because all the values are now in terms of the probability distribution and the values are ranging from 0 to 1, and it can take any float values as well. So what I am doing, I am taking the argmax in the channel in the last dimension. So that means in the channel dimension, I am taking the argmax. Now what argmax will do, whatever highest value it will find. So in a, let's say, if I just give you a numerical example, let's say you have a data like this, 0, then over here you have 0.9, over here you have 0.0001, then over here 0.000 something 1, 0.005, like this. So if you pass it through argmax, it will keep everything as 0, and whichever had the highest value. So over here this had the highest value, so it will put 1 corresponding to this, right? So argmax job is basically it will try to find that whatever highest value is there in the array, it will put a 1 corresponding to that. Rest of the other places it will put 0. So this is what argmax basically does. Then I'm taking the predicted masks, and then the last dimension over here. So the new axis I'm creating, because we know that we had a mask which is of shape 128 cross 128 cross 3, and the neural network basically predicts it in the form like we feed data in batches, right? So if I just open this, we feed data in batch size multiplied with the image dimension. So we need to remove this batch size dimension. So that is why we are writing that tf.new axis. So this was basically a new axis added to the images. So this new axis will be chopped off because we do not need, because we want to see that at a single image level what is happening. So to visualize this, we are just removing this dimension. And then I'm taking the prediction mask 0. So that means whatever data is coming, I'm taking the first instance of that. And then definition of display, already we have mentioned that we will display the input images, the true mask, and corresponding to that we have a prediction mask coming out of the unit architecture. So simultaneously there will be a 3 images. One will be input image, one will be true mask, and one other one will be the predicted mask. And sequentially we'll try to see that how they basically look like. And this is just a for loop because I will run it for, let's say, 3 to 4 times. We want to see for 3 to 4 images. So therefore, I'm writing a for loop to create those images one by one. And then to compile everything together, I have created another function. So that is show prediction. It will take data set. In our case, we'll feed the test data. Then if data set is basically a test data set, I mean, if data set has certain attribute, so in our case, it should be a test data. So then what I will do, I will take the image, I will take the mask from the data set, and then I will try to predict the mask using the image. That means the image of the cat and dog that have been given in the test data. And what model will you will use the unit model, because we have trained the unit model to predict the masks. And then I will use the display function to generate the image of mask, generate the image, generate the uh, uh, graph, generate the instance of the image, the true mask, and then the predicted mask. And for that, I am using the create mask function that we have already discussed over here. And then it will, I'm just writing another for loop, and I'm passing this test batches, because already we know that uh, uh, we already created 2 set of data. One is the training batches and another is the testing batches. So the training batches were used basically to train the model, and test batches were used to validate the model at that particular time. Now we'll be solely using the test data to test our model. And then I can show that how many batches are there for the test set. And then I can show the predictions. So the data that we are feeding over here, already I told that it should be test data. So I'm putting test batches, and the number of images that I want to see, that the number of for the number of true images, that how the true mask looks like and the predicted mask looks like. So I'm considering that number of images that I will consider is 5. So I can just run it. Now it will take some time to create the batches uh, and the prediction also. So you can see that number of batches is 11. In the test data set, we have some thousands of images, and then we took a batch size of 256, and then we can calculate the what should be the number of batches in the test data. So now you can see this is an input image of a dog, right? And this is the true mask. And this you can see that this have been predicted by the model. So clearly you can see that it tries to resemble some sort of an object to be placed here, that is in some sense it is correct, but in more specific way you can see that the boundaries, it is not able to predict the boundaries. It is not able to predict the, for example, for the dog has some sort of a chain over here, so which is also referred in this particular image as well in the true mask, and a locket, but it is not able to predict, but it tries to some somewhere it is tried to predict that there is an object. If you increase the number of epochs, then the model may perform well. So over here as well, you can see this is the true mask and this is the prediction that you are getting. So this is another cat, image of cat. So this is the prediction. So over here still some comparable results you can see, but in a not in a specific way, the results are quite poor. But the positional argument, if it is so far as concerned, the positional argument is concerned, you can see the position of these masks, or at least the structure of the object is more or less at the same position. So that means it hasn't shift invariance property. So then we have an image of cat. So you can see here your model is miserably performing very poorly. So another instance could be there is a dog sitting in a bucket, and this is the prediction result that you can get. And so far as the numbers are being considered, yeah, so we tried to plot 5 images. So therefore, these are the 5 images that you can see from this particular function. You can increase the number of images and then you can analyze for more such cases as well. So this is how you can create a unit architecture, and then actually you can analyze that how the model basically tries to predict the masks. So if you increase the number of epochs, so obviously we can think of that the model prediction will uh, it may improve, it may get improved. Okay. So this is the first demo that so already I think I have shared the file in, yeah, already I have shared the file in the GitHub profile, so I don't have to save it. So I can disconnect the runtime. So this is the first demo. Okay. The next demo that I'm going to present is autoencoder. So already we discussed the problem. I have certain images. I will add noise to that image, and then I will train an autoencoder or deep learning architecture so that given these noisy images, I can produce the cleaner version of these images. So now let us start simulating the code. So I'm importing the libraries. Already you know, you are familiar with this, that NumPy is for the array operation, matplotlib is for the data visualization purpose. We use matplotlib to plot the data. Then I'm importing, then I'm calling the keras, and from keras I'm taking the layers, as because within layer we have font 2D, maxpool 2D, etc., etc. We can use them. And from keras.dataset, I'm taking mnist. So in the last class also we worked with mnist. So I can use mnist again to create the convolution autoencoder architecture. And then I need this keras.models, keras.models, and from there I am importing model to create a functional API based model. In the unit architecture also we have seen, while creating the unit model, the argument that we had used over here is unit model equals to tf.keras model. So you can see the functions that we are using is model, which takes different inputs, different arguments. One is the what should be the input of the model, what is the output of the model, and you can name the model as well. Okay. So far as the data processing is being concerned, already this thing also we have already seen that the MNIST data set is in the shape of 28 cross 28 cross 1. Effectively, it is 28 cross 28. We do not write 1 as the third dimension because it is intuitive that if you are not writing anything after 28 cross 28, that means it's a single channel image. But your neural network model does not understand that. So specifically for neural network, you have to mention that it is 28 cross 28 cross 1. So that means the channel information has to be specifically mentioned. So that is why what I am doing is I am taking the array, I am normalizing it because the images are having value in the range of 0 to 255. So I'm dividing it with 255. Then I'm reshaping to the shape of 28 cross 28 cross 1 to specifically mention that the channel dimension is 1. This is a single channel image because your model has to know that whether the data is single channel input, or your data is 3 channel, or it has more channels. And then it will return the array. Fine. So this is for processing the original clean images. Now, on top of this clean image, what I want is I want to add noise such that we get noisy representation of the clean images. So to add noise, I have created another function that is definition noise, which will take the clean images, which is basically array. And then I have put a noise factor of 0.4. So, which means that I'm scaling the variance with a factor of 0.4. And then what I want is I want a noisy array, which is basically clean signal, which is named as array, plus the noise factor, that means 0.4, it will be multiplied with. And we are taking normal distribution that I have already talked about. We are taking normal distribution. And what sort of normal distribution we are using? We are using mean 0 and variance 1. And we have to generate the similar dimension so that the dimension of or the normal distribution output size should be same as the size of array, so that we can do the addition. Otherwise, if the dimension mismatch is there, then it will throw an error. And then what I will do, I will take, I want this noisy array to be returned because it will give me final noisy representation of the clean data. And I want every data to be clipped in the range of 0 to 1. Why 0 to 1? Because you know that when you normalize the initial clean images with a factor of 255, each and every data will be bound in between 0 to 1. That we have showed in the LeanET 5 code as well. That all the data, if you normalize them, it will be ranged in between 0 to 1. So that is why we are clipping every value in the noisy array as well in the range of 0 to 1. Okay. And lastly, I want to display the clean image as well as the noisy image. So therefore, I am displaying two arrays. So the function takes two input. One is array 1, another one is array 2. And I will try to visualize 10 such images. So therefore, I will take 10 such cases. And then here it is just a for loop to plot all those 10 images. This is very easy. You can see it at your side as well. So let us just start running this particular code snippet. Yeah, fine. So the next is we want to prepare the data. So first what we have to do, we have to load the data. Already we know we are using MNIST dataset. So what I have to what I have just to do is we have to call the object MNIST and then load data. So it will automatically load the data in training data and testing data. So as far as the label is concerned, as because I am not bothered about the class, as because this is not a classification problem, this is a denoising problem, I do not require the labels of the images. So that is why I have just kept blank spaces. So this basically allow you to not assign those labels into a certain variable or skip those data. So as because I don't need the labels, so I have not put anything over here. Then I have to normalize and reshape the data. So that is what written in the pre-processing function. So I am just feeding this train data into pre-process function. So it will give me the processed output or the normalized output. And test data also I am doing the same. Then I'm creating the noisy representations of the clean data. So for that, I'm calling the noise function, which will take the clean images from the train data and test data. So I will create the noisy train data and noisy test data. Fine. And then I want to display those images. So therefore, I will call the display function. So now let us see. So now you can see that we had an image of 5 and now it is buried into Gaussian noise. Similarly, we had an image of 2, which is buried into Gaussian noise. And so as in each and every cases, you can see that your information is now buried into noise. And the problem statement that we have been given is, given these noisy images, can we produce these clean images back? So that is the problem. And we want to address the problem using autoencoder architectures. So to say, this is a denoising autoencoder architecture. So the denoising autoencoder architecture now we have to simulate. And in the last class, I showed you that how to create the models in a sequential API. So in this class, I am focusing on functional API. So functional API, how you can code is basically, in the last class, we wrote something like this. We wrote model dot sequential. And then within this definition, we were adding font 2D, blah, 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 then max pool 2D. So likewise, we basically kept on adding the layers. So this is one way of creating the model. And today I'm showing the another way of creation of the model, that is through functional API. So in functional API, how you write the code is basically, for each and every layer, you manually pass the data by yourself. For example, this is the input. You can write layers.input and you can define the shape. In our case, this is 28 cross 28 cross 1. You have to specifically mention this one because your model has to know that whether your data is a single channel data or it has a multi-channel data. Then we have to create the encoder part of the autoencoder. These things you already know that autoencoder has two parts. One is encoder decoder, and the end of the encoder is also referred as the bottleneck part. Then, as I was talking about functional API, so in how we write code in functional API, we are writing layers.cont2d. Number of filters that I'm considering is 32. Kernel size is 3 by 3. Activation function is relu and padding is same. So each and every point already you know that what is the significance of these lines, that 32 is filter dimension, 3 cross 3 is kernel dimension. Relu function, you know, it basically helps to reduce the problem of overfitting or vanishing gradient. And padding same means your output should be of the same shape as the input. So therefore, even if you do convolution operation, your size of the output should not decrease. If you put valid instead of same, then after convolution, your output's dimension will decrease. But if you put same, so that means that even if you do convolution, your output shape will be same as the shape of the input. And now in model.sequential, you see in model.sequential, we did not write anything after this con2d. So it was like this, the model was by itself, it knows that if you feed a data, it has to pass sequentially through all these layers. So specifically, you do not have to mention anything here. But in case of a functional API code, you are manually putting the input data after each of these layers. Then the output that you get, it is X. It is passed through a max pool layer. And again, you are feeding the input to this max pool layer by yourself. You are specifically mentioning that what should be the input to this max pool layer, that is X, which you get from the previous convolution layer. Had it been the case of a sequential modeling, you don't have to write these things specifically, because that time model itself knows that I have to pass the data sequentially into the layers one after another. Then again, I have kept a convolution layer, a max pool layer. So this is the end of the encoders architecture. Now I have to go for the decoder architecture. So encoder architecture, we know that in general in encoder architecture, the size of the input decreases, as because you can see we have max pool layer. Max pool layer basically decreases the size of the input. Now at the output side of the decoder, so see over here in the encoder part, the size of the input is decreasing. The size of the input is decreasing in the encoder part, and at the bottleneck, whatever output that you have got from the encoder part, now you have to increase the dimension or you have to upsample it. So therefore, in the decoder part, instead of using conv2d, we will use con2d transpose. This con2d transpose basically does the upsampling operation. So that means it has to increase the data dimension. So therefore, you can put con2d, and in between inside that you can again write these things like 32, 3x3, stride 2, relu. So already I think you guys know that how to write this functionalities inside the con argument. And in this way, I can simulate the decoder part. Now I have to create the final autoencoder model. Now how this particular autoencoder object will know that from where to start and where to end. I can end at this position as well. I can end at this position as well. Even I can end at this position as well. So for that, I have to specifically mention with this command that model, which will take the input of the architecture and the output of the architecture. So input is named as input, and just to specifically mention, I can write this as or I can write OP. So you can see that I'm feeding specifically the input and the output, and I'm passing those two arguments in the model command, which will create the autoencoder architecture. And then I'm compiling the model with Adam optimizer. And as because this is not a classification problem, I can choose anything like MSE, MAE, anything. Even I can choose this cross entropy losses as well. And then I want to print the summary of the model. So you can see that you had initially 28 cross 28 cross 1. Then you have done convolution, then max pool, data dimension reduces. Then again convolution, as because you have kept same as the padding information. So the convolution output is same as the previous tensor dimension. Then max pool layer decreases the dimension. Then you do con transpose 2D. So from 7, it has increased the dimension twice. From 7x7 to 14x14. Then again, it increases the dimension twice, the spatial dimensions, not the channel dimension, that 28x28. And at the end, as because I need a image of 28 cross 28 cross 1, I have kept another convolution layer, that is layer.conv2d with kernel, with number of kernel as 1. So you see that your final output dimension is, channel dimension is 1. And the padding information is same. So therefore, previously it was 28x28. So now also it is 28x28. Okay. Now we have got the autoencoder model simulated. Now we can train the model. So I have to feed the, so in this case, what would be the training data. So the training data will be the noisy data. So the training input will be noisy data, training output would be the clean data, because the reference data is that the model predicts something and the model will calculate a loss between the predicted output and the clean signal. So that is why you see X, which is basically input to the model, is noisy train data. Y is train data. So that means is the clean part with which the autoencoder has to calculate the MSE or any sort of loss that we have defined earlier. And then it has to update the weights using gradient descent rule. And subsequently, it will learn how to create the clean image, how to generate the clean images given the noisy data. Then epoch, for 30 epoch I am running, batch size is 128. Shuffle means in each and every epoch, when I will feed the data, I am taking the data in a batch. And then while feeding the data, I can shuffle all the data. You can keep it false as well. That will not create much of a fuss. Then we are putting the validation data, and in the validation data, I am again feeding the noisy test data and test data. So that means the noisy data and clean data. Now we can start fitting the model. So I think I'm running on GPU here. So it will not take much of a time because the image dimension is quite low. So the processing time will also be reduced. Okay, so the epochs have now been completed. So you can see that at the end of the epoch, you have achieved a very good validation loss 0.0850. So you can, again, the main point is if you can increase the number of epoch, it will even yield very less loss values. So you can see the loss and accuracy curves by your own. I have just given the code. You can uncomment them and plot. That is not a big issue. So now what we have to see, that we have to do the prediction on the test data. And then we have to see that how the original, how the noisy test data basically looks like and how the predictions basically looks like. If I just run this, you'll see that initially we had an image of 8, which was buried into noise. And when you feed that data into autoencoder basically substantially it reduces the noise from the image. But still you can see there are some bloody effects are there. You got somewhat a 4 or 9 or whatever it is, I don't know, probably a 4. But still the image is quite bloody. It is because you have kept very low number of epochs. One reason is basically the image dimension, the image resolution is poor, that is for sure. But another point is, had it been trained for a larger amount of epoch, so that at that time the model would have learned very well from the data and it would have created quite a sharper images as well. But as because is a, for example, in this case, the bloodiness is quite more than this one. So over here 9 is quite sharp, but this one, this 4 or 9, whatever it is, this is quite bloody. So this is the second uh, demo that I had mentioned. So we have seen that how to simulate a convolutional autoencoder architecture to perform a denoising operation. Then we have the last demo, that is very small demo. Let me go to the repository. GG SPM. Yeah, NPTEL RNN. So this would be RNN. So over here, what is our aim is, we have seen something like this in our day-to-day life, that stock market data, like something like this, you see it for a span of, let's say, 1 year, and there are several financial consultancy agencies are there, which basically tries to predict or give some prediction that probably in next year whether it will go in the up direction, or I mean there would be profit or there would be loss. So that means based on the previous data that you have seen, this is a time series data. Because at each and every day you uh, take the amount of loss or profit, whatever basically you get in a particular stock, and then you collect all the data over a year, let's say, and you try to analyze the data, and based on this data you try to predict what will be the output, whether it is a profit or loss in the next year. So for these type of tasks, the type of neural network that we use, that is called recurrent neural network, which basically specifically created to handle the sequential type of data. So therefore, we'll be using one such case that which is called LSTM, or which is a specific version of an RNN architecture. So you can start by invoking all the libraries that we have already seen in several cases, that is TensorFlow, Pandas, Matplotlib, Sequential, Dense, LSTM, because we need LSTM. So I have specifically written that from these dot layers, I need LSTM. You can go with any sort of method. You can just put TensorFlow keras, you can import TensorFlow.keras, and then while writing the code, you can write tf.keras.layer.lstm. There are several ways to write the code. So just do not stick to a one convention. You can venture out different convention of writing the code. So let me just run this. And I need a data set. So previously we were working with the standard data sets like MNIST data set. Then we had what do you call Oxford data set. But in this case, as because I was not able to find a standard data set, I just got a CSV file, which is basically an American aviation agency's data. So this basically comprises that at each and every day, how many person basically gets into the aircraft. So it has a year-long data. So from those year-long data, we'll try to predict that given certain amount of data, can I predict that what will be the amount of people who are boarding into the aircraft. So to create the data set, I need to get a I need to get a array or get a data frame. Then I am using look back one. So what does this look back one means? This means something like this. So let's say you have y0, you have y1. So what you will do using this y0, that means you're looking at a single data. Based on this single data, you will predict the next one. Then based on this one, you will predict y2. So this is what look back one means. You can play with this value as well, and then you can create your own results as well. But for the moment, let us not go into this nitty-gritty details about it, and let us just create. We need two data sets, because one which will use to uh, train with, which will basically go as the input of the model, and one which will basically the prediction of the model or the true prediction of the model. So that is why I need an X and Y, which I instantiated as a list, empty list. And then I will, using this loop back one, I will fill those data into data X and data Y. And that is why I have written append. What append does, append basically, as the name suggests, append basically appends each and every data point one after another in the for loop. So I can run this thing. And then you see the database name is airpassengers.csv. So we need pandas library. So I hope I have, yeah. So see, from pandas, I'm importing read CSV. So we need pandas library to read this CSV file. And the engine that I'm using is a Python 3.7. So I'm referring Python. And then the data set, the read.csv pandas basically give you the output data in a type called data frame. So from those data frame, I need to extract the values. So therefore, I have written data frame dot values. and I want all this data to be in the form of float 32. So I'm typecasting all the data into float 32. Okay. And then already we have discussed that what is the importance of normalization and all. So we have normalized the data. So for normalization, we have used min-max normalization. What does min-max normalization does is, let me just show you. So if you have a data X, min-max normalized data, so Xn is the normalized data, it will do something like this: X minus X min divided by X max. So what will be the range of the what will be the range of Xn? So let's say Xn when X equal to X minimum. Then what will happen? We will write X min minus X min divided by X max minus X min. So you see the numerator is 0. So therefore X1 will reach 0. And when X equal to X max, then what will happen? Xn will be X min, X max minus X min divided by X max minus X min. I'm just putting the corresponding X value over here. So that is why I'm writing when X equal to X max, just replace X with X max. And then you can see numerator and denominator both are same. So they will cancel each other. So you will get the value as 1. So therefore you can see Xn is basically ranging from 0 to 1. So again, the normalization output will range in between 0 to 1. So this is another way of doing normalization. Initially, for the image cases, we saw that we were directly dividing with the highest value, that was 255. In this case, we are seeing another sort of normalization technique that is called min-max normalization, which ranges the data in between 0 to 1. So I directly have wrote 0 to 1, and that this is the explanation that why I have written 0 and 1. Okay. After that, you have to fit into this scalar transformation on the data set. Fine. And I need to split the data. So 67% I'm taking for the training data, and rest of the data I'm taking for the testing data. So I'm creating train and test in this particular part. So already I told you that I will be using loopback equal to 1, and we have already created the create dataset function to create the X train and Y train. Sorry, X train and Y train and X test and Y test using the train data and test data that we are getting from here. Then I'm reshaping all the data because over here also the LSTM works. The LSTM takes data in this particular fashion. One is the dimensions. In case of CNN, the dimensions were batch size multiplied with images height, width into channel. So this was the inputs. In this order, CNN actually takes the input data. So each and every model has its specified structure. So LSTM has also a specified structure. This is samples, then time steps, then features. So as because this is a single channel data, because we have only a single stream of data, so that is why time steps equals to 1, and rest of the things are train.shape 0. That means it is the first dimension of the input data, and this is the second dimension of the input data. Now we can create the LSTM model. So for creating an LSTM model, I am considering a sequential model because I'm not going to write a complex model over here. So therefore, I will just add add one LSTM layer. You can again create a complex LSTM model just by stacking this same thing again and again. But let us not do that for this particular demo. So model.add. So what we will add is LSTM. Number of LSTM unit is 4. Input shape you have to define. So already we have given the input shape. And then at the output, I need to predict the final data. So what I have initially told that given one data, I'm predicting the next data. So therefore your output dimension will be 1 because you are predicting only one data. So that is why you can see that tens of 1. Then you compile the model using MSE and optimizer as Adam. Then you feed the model with training data, X-train, Y-train, epochs, number of epoch is 100. Batch size I have kept as 1. You can increase the batch size. And verbose is equal to 2 or 1. It doesn't matter. It basically enables the printing option. So now you see that the model has started learning. And as because this is a very small data set, it will take probably within a minute, it will complete 100 epochs. So you can see that we have completed 100 epochs. Now we have to investigate how your model is performing. So that means you have to do the prediction now. So what I have done, I want to see the prediction for the training set as well as for the testing set. So that is why I have fed both X-train and X-test. And subsequently, I got the testing results. And then I just have done some matrix manipulation so that I can get the, because you can see that we specifically added, we have reshaped the data into this particular format. But at the time of testing or at the time of plotting data, I do not need this dummy dimension. So for that, again, I have to go back to this dimension. I have to remove this one. So I have to get sample comma features. So for that, I need a transformation. So this time I did a forward transformation of reshape. Now I need a inverse transformation. That inverse transformation, what it will do, it will remove this particular dimension. Okay. So you see that scalar dot inverse transformation, it will just inverse that transformation. It will just revoke that dummy dimension so that we can plot them easily. And then I can calculate the RMSE. I can calculate RMSE for the training data set, testing data set to know that how well I am predicting the data for the test and train case. And then I want to plot the data. And for plotting the data, it is just as you have the training data, you plot the training data at the same, plot the training data in a graph. And on top of the training data, you plot the model prediction. So over here, you see train predict plot. We started with an empty array, and then subsequently we are adding data one by one. So initially we wrote np.nan, so that means each and every data. So over here all columns are selected, so that means each and every data is filled with nan. Nan means not a number. And then using that look back, that means given a single data, I will predict a next data. So given this, I am filling all the data. So see look back and then the current index plus look back. So that means if the current index is 0, index is 0. So that means, or say current index is 1. So it would be 1, 2, 1 plus 1. So that means 2. So that means it is creating a look back situation. Same thing I am doing for the prediction case. And then I am plotting both of the training prediction and the test prediction at the same time on the same graph. So now let us see. Yeah. So see this part till this orange part, this was the training data. So you see your LSTM model is very well predicting the training data. so as for the testing data as well, where the green lines are coming. So that means from this part onwards, if I just copy this, create an page over here. Yeah. So see, this part to this part, this was the training data. The blue one was your X train. And this orange one, your predicted output for training data, as because this part refers to the training data. Now over here, this part refers to the test data. This is your blue one is your X test and green one is your model prediction. And you can see your model is very well predicting the data. There are some glitches. Probably over here, the amplitude differences are there, but it is able to capture the trend similar to the original one. You can see the trend is same. Maybe the amplitude is not matching, but the trend is same. And in majority of the cases, like in case of data predictions, so as the stock market data is concerned, the trend is very important rather than the amplitudes. So with this, we have completed the 3 demo. One is the RNN one is the unit based image segmentation, and another one is the convolutional autoencoder based denoising method. So if you have any query, then you can ask. And this is the final class from my side. So probably the other TA will have one more class, but this is the last class from my side.
Yeah, hi Arka, this is Someshwar here.
Yeah.
Yeah, no question as such. This was really, really amazing and wonderful session. And the journey was so good to be with you throughout this NPTEL course. So on behalf of all the students, I want to express my gratitude and thanks to you. Thank you so much for being with us and guiding us through this course. Thank you so much.
Yeah, welcome. So you can put the feedback in the course forum as well, so that because because we are teaching, we are also doing the TA-ship in the course. It is great for us to know that where we can improve while delivering the lecture. So please give a feedback in the course website as well.
Absolutely, I'll do that. I'll do that, Arka. So this will be basically an NPTEL forum, right? We
Yeah,
can
yeah.
just post
No,
the link here, then probably I'll just.
you can, there is a section. If I just open this,
Mhm.
uh, there is a survey probably they have given this. You go to problem solving. Sorry,
Mhm.
you go to problem solving. Then you
Mhm.
see one is the recording and another one is the problem
Survey,
solving session survey. So when
right,
you hit the thing, it will open a Google form,
right.
right? So here you can put the survey.
Absolutely. Then I'm doing it right away. It's fine. Yeah.
Yes, the same I will do also. And thank you for your thank you, sir.
Yeah, thank you. Thank you. Okay, so now I think I can stop recording.